Hello everyone, I welcome you all to Physics Wala, and in this session we are going to start our new chapter of physical chemistry, which is thermodynamics. As you know that this particular chapter is a very important chapter from chemistry point of view, because in this particular chapter it's a core chapter of physical chemistry. In this case we are going to discuss n number of calculations related to the entire part of thermodynamics, and we are going to learn some interesting concepts how we can predict a particular possibility of a particular reaction. So in this particular session, this is the first lecture of the chapter, which is thermodynamics, and we are going to discuss about the basics, only the basics related to this entire chapter, which is thermodynamics, because there are multiple definitions related to this entire part. First of all, we have to be very familiarized with all the concepts related to thermodynamics. Then only we can go towards the next part, which is the formulation and calculation related to the thermodynamics chapter. Now I already told you that this is a core chapter of physical chemistry, so we are going to discuss different type of concepts. First we are going to start with the introduction part of this chapter. Then we are going to discuss about the state as well as path functions. Then we are going to discuss about different type of thermodynamic processes as well as some ideation related to work as well as heat. I hope this portion is clear, although it's nothing that much relevant, but we are going to discuss that part. Now first thing which comes to your mind whenever we talk about thermodynamics is, what is the meaning of thermodynamics? What is the meaning of that term? So in that case I'm going to start with the basic part. I'm going to start with the basic definition part of thermodynamics. So basically the term thermodynamics, this chapter will come in your physics part also, somewhat related to the same chapter, which is we are going to discuss in this particular session of chemistry. Physics part is almost same, but some other assumptions are there, some other sign conventions are there, and definitely the system on which we are going to work is entirely different. So let's start with the first part. So basically in chemistry, whenever you have unknown reaction, let's say we have the reactant side. Let's say I have certain reactants, unknown reactants, and I am reacting them together in a specific conditions to form a particular product. So to understand this type of reaction which is unknown to you, like this entire part is unknown to you. So this is the reactant side which is converting into the product side. That is the chemical reaction. So let's say you have 2 or 3 chemicals, you mix them together and you are forming a product. So what is the basic question which comes to your mind? First question which comes to your mind is the possibility of reaction. First question which comes to your mind, whether this reaction is possible or not, or I can say spontaneity of the reaction. Or I can say spontaneity of the reaction, whether this reaction is possible or not. So that question actually deals with the first part, which is thermodynamics. So this question can be answered with the help of thermodynamics. That's why this chapter is a very important. It's one of the part of the chapter which is thermodynamics, that we are going to deal with the spontaneity of the reaction, whether a particular reaction is possible or not. Now the second question, after completing the entire part, you know that reaction is possible and you mix 2-3 reactants together to form a particular product. Now in that case you need to know like the amount of reactant required as well as the amount of product which is going to be formed. That part, like what is the amount of reactant required and how much amount of reactant is going to be converted into the product, that part actually deals with the next portion, which is your equilibrium chapter. So in the case of equilibrium chapter, you need to understand a basic type of reaction, which is a reversible type reaction. We are going to discuss about reversible processes as well in case of thermodynamics, but that part, equilibrium, deals with the reversibility of the reaction and talks about the amount of product which is going to be formed after the establishment of equilibrium. Now last part, you know that reaction is possible, you know that whatever amount of reactant is required to form a particular product at the condition of reversible reaction. when the entire system is going to attain the state of equilibrium. Now next question which comes to your mind, like I know the possibility of the reaction, I know the amounts we are dealing with, but next part, whether this reaction is going to be completed in 5 seconds or 5 minutes or 5 hours, or I can say 5 days. So that part is basically related to the speed of reaction, or I can say rate of reaction, rate of the reaction. And that question can be answered with the next chapter of chemistry, which is chemical kinetics. So basically I can say that these three parts are related to each other. First part is thermodynamics, then we have equilibrium, and last part is chemical kinetics. They are very interrelated to each other, because most of the formulations, most of the possibility of the reactions are exactly same in each scenario. Now if I talk about the term thermodynamics, you can clearly see in this case we have two terms. First one is the thermo part, and the next one is the dynamics of the reaction. So basically thermo means heat exchange. So in this particular chapter we are going to discuss with different type of heat exchanges which are occurring in a particular process, and what is the formation, or what are the different type of reactions where we need this kind of heat, or I can say this kind of energy. So this part is somewhat related to the energy exchange, or I can say energy change. So the entire part of thermodynamics more or less talks about the different variations of energy and how these type of energies are going to be converted from one part to another part. Now in this particular case of thermodynamics, if I talk about a very simple analysis of thermodynamics, first part is related to the introduction. I can say first part is related to the introduction of the entire chapter. Now what comes inside the introduction part? In this case you need to learn definitions as well as their formulas. So in this session only we are going to discuss different type of definitions, different type of terms which are related to the chapter which is thermodynamics. Now after completing the introduction part, we are going to move towards the next portion, which is a very interesting as well as very important portion of this chapter, which is first law of thermodynamics. Although there is one more law which is zeroth law of thermodynamics, but that part is very easy to understand. We are going to discuss with the first part, which is first law of thermodynamics, and trust me, this is the most important one part, because in this case you are going to deal with delta U, which is internal energy change. You are going to understand what is a delta H, enthalpy change, and work done in the process. So entire calculation, most of the important calculations comes under the first law of thermodynamics. Then along with that we have second law, and I can say third law of thermodynamics. If you have completed the entire part, then there is one important concept which is a sub part of these two laws, I can say, which is entropy concept. So we are going to discuss about the entropy concept in case of thermodynamics. And last part, which is a very easy, I can say, that part corresponds to thermochemistry. So we are going to utilize the energy change with respect to different type of reactions. So this part comprises of different definitions as well as simple formulation of Hess law, you can say. Then we are going to discuss Born-Haber cycle also in this case. So this part is the most easiest one in the entire part of thermochemistry. So I hope this portion is clear to everyone. This is the overview of the chapter which we are going to discuss in the upcoming sessions. So basically we have 6 sessions for thermodynamics, and I'll try to make sure that everyone gets the idea of thermodynamics as well as everyone gets the idea how to deal with the calculations, because I know for most of the students thermodynamics is the I can say toughest chapter because it comprises of different formulas. For one question you can derive different quantities with the help of information whatever is given to you. Okay, so let's start with the first part. What is the introduction part of this chapter, which is thermodynamics, and what are the various types of definitions we are going to deal in this chapter. Okay, that is your lecture 1. So first part is, you have to understand whenever we are talking about any thermodynamic change, in that case I need to understand that whatever quantity I want to observe, I need a particular system on which I can see the change. So there are 2-3 terms which you need to understand. First one is the system, next one is the surrounding, and last part is your boundary. So if I talk about the system part, so basically in this case, a system is the specified part of the universe which under investigation or observation. So basically that particular part of the entire universe where you want to see the change in the properties, thermodynamic properties, whatever you are going to study, that part corresponds to your system. There are different types of system also, that part also we are going to discuss, like what is the various kind of systems. Next part, you can see in the universe we have already picked the system on which we are going to see the change. So the rest of the part of the universe excluding system is actually known as your surrounding. Okay, so let's say for chemistry lab, so if you are present in the chemistry lab, you are doing certain experiments and you have taken a particular system or a container where you want to see the change or where a reaction is happening. That is your basically system. The rest of the part where you can analyze the entire analysis, that part is the surrounding. It's not like that you are doing experiment in India and you can see the surrounding will be in the US. So that is again a specific area. You need to understand the difference. You need to correlate the boundary also, so that you can entirely observe the system. So let's say you are in the chemical lab, so that entire chemical lab will be your surrounding, other than the apparatus or the workstation where you are performing the reaction. That part is basically your system. So this is the meaning of system as well as surrounding, and the entire combination part of the system and surrounding means we are talking about the universe. Okay, not the actual universe. Okay, so if I talk about the classification of systems, in that case we have 3 types of system. First one is known as open system, next one is we have closed system, and last one which is known as the isolated system. So what is the meaning of this open system term? So basically a system is said to be open if you can see 2 changes. First part, if you can exchange the matter between system and surrounding, and you can actually exchange the energy part between system and surrounding, that part corresponds to your open system. So basically 2 changes can be visible. There is a change of a matter which is happening, as well as there is a change of energy which is also happening in the system. So let's say I'm preparing a cup of tea. So in that case I need to use a simple pan, I can say, where I can boil the water as well as your milk. So in that case, when that container is open, you can see whatever amount of water is present. After heating, it's going to be converted into vapors, and if this container is not closed, if it is open, then definitely you can see some amount of water vapors are leaving the surface of that pan, and they are converting into the gaseous phase. That's why you can see there is a reduction of the amount. You initially started with 1 cup of water as well as 1 cup of milk, and eventually after the entire formation of a simple cup of tea, you will get a final 1 cup only. But initially you had started with the 2 cups of 1 cup of water and 1 cup of milk, but eventually you end with only 1 cup of a tea, which corresponds to the exchange of matter. Matter is changing, matter is exchanging between system and surrounding. In the same way, the heat is also dissipating outside the system, which shows that we are talking about the open type of system. Now let's say in the same process of the formation of a tea, what happens? I have closed that the open lid of that container. It means now energy can exchange, energy, because the container is not isolated, energy can easily exchange, but now whatever water vapors are leaving, they strike to the surface of that lid, and eventually they will come back to the container itself. It means in that case you can see there is a exchange of energy happening between system and surrounding, but there is no exchange of matter now. That type of system is actually known as your closed system. So in this case you can see that energy is exchanging between system and surrounding, but now matter is not exchanging between system and surrounding. Now we have a third type of system. So basically in that type of system, neither the energy is going to exchange between system and surrounding nor your matter part. So basically a system is said to be isolated if it can exchange neither your matter nor energy with the surrounding. I'm not saying that we have a perfect isolated system, but you can consider that thermos flask generally we use in our daily household, that thermos flask is approximately equals to the isolated system, because when you put the hot tea or you can say hot beverage inside that container which is your thermos flask, so in that case you can see after 2, 3 or 4 hours also that container that the material whatever inside that hot beverage is actually hot again. So you can see the energy exchange as well as matter exchange is not possible in that kind of system, and this is the most interesting one. So basically in this type of system you can say that no matter is exchanging and no energy is exchanging. I hope the first part is clear. Now there should be some difference between system and surrounding, how I can differentiate system as well as surrounding. So that differentiation is actually known as the boundary of separation. So in that case the next part is basically your boundary. Always remember, anything which separates system from surrounding is actually known as your boundary. I know that you all know these type of terms which are very easy to understand, but this is the first part of thermodynamics. You need to be familiarized with all the concepts like whatever we are going to discuss in case of thermodynamics. Now boundary can be real, which can be easily visible, or it can be imaginary, which is not that visible. So always remember, it can be real or it can be imaginary. For example, I have a container which is, let's say, this beaker. In this beaker I have put some water inside it. Now as you can see, this container is providing a clear separation between the surrounding part and system part. So you can see this boundary of the container is actually the real boundary. Now let's say this water is actually also present with air. So that air is not that visible. So you can see again that part which is present in the upward direction of this entire container where the water is present. So that upside part is not that visible. You cannot see a difference between these two parts. So it can be imaginary also, but you have to differentiate that whenever we are talking about the system and surrounding, a boundary is always present. If it is visible to you, it's very good. If it's not visible to you, then you need to consider that boundary is definitely there, but it's a imaginary boundary. I hope this portion is clear to everyone, and we have already talked about the system, surrounding as well as boundary, because now we have to work on the system. Whatever reactions are happening, they are happening inside the system also. So by default, always remember that whenever we are talking about the chemical reaction, they are not hypothetical terms, because most of the time when we discuss this entire chapter, after some lectures, students gets confused, like, sir, like what is happening, why we are talking about the compressibility of gas, why we are talking about the expansion of gas, why we are talking about this type of work done, why we are talking about the internal energy change. We are not getting it, like what is the system inside that. So basically always remember, we are talking about the chemical reactions. So chemical reactions which are mostly dealing with the gases. So in that case of introduction part, let me tell you that whatever we are going to discuss, whatever we are going to discuss in this particular part is mostly related to the reactions of gases. We know about the entire part of gases now after completing states of matter chapter. So we have a particular idea like what are gases and how a particular reaction is going to take place. You can consider any type of reactions, and mostly in this chapter we are going to discuss about the reactions which are happening for gases. Either we are going to compress that gas, or the gas is going to expand, a different type of chemical is originating in that process, and whatever energy changes are happening, that corresponds to your part which is thermodynamics. I hope this entire portion is clear to everyone. Now, if I talk about the thermodynamic properties, basically we have differentiated properties into two parts. First one is actually known as your intensive property, and the next one is known as your extensive property. What is the meaning of this term, intensive as well as extensive? So we have different type of thermodynamic properties. Now in that case, if I talk about the intensive one, so basically all those quantities, or I can say all those measurement things which on bifurcation gives you the same kind of result, those properties are actually known as intensive property. It means they are independent of the quantity of the matter which is present in the system. So let's say we have a system, I have put it some chemical inside that particular part, and I'm considering a particular calculation, either the calculation of temperature, either its mass or its volume, whatever it is. Now on bifurcation, if I can see the same value every time, it means that property is intensive. It doesn't depend upon the quantity of matter whatever taken inside the particular system. So always remember, these are the properties which are independent, which are independent of the quantity of the matter present inside the system. And the simple arrangement of that particular, how to understand that it depends upon the amount or not, it's very easy thing. You just have to bifurcate that particular amount whatever you have taken, and then calculate the same property. If the value is exactly same, then you can see that this property is an intensive property. For example, if I talk about the density of water, very simple example. Let's say I'm talking about the density of water. Generally we take this density of water as 1 gram per ml. Generally this value is 1 gram per ml. So let's say I have taken this container, this is a beaker, and in this case I have a 50 ml of water. 50 ml of water is present. Now let's say I am bifurcating this entire part into two small containers. So this is one container having 25 ml of water, and in the next container again you have 25 ml water. Now in both the cases, can you tell me the density of water? Yes, in first case this density of water is nothing but 1 gram per ml, which is true. On bifurcation, in this case you can say that density of water is going to remain same, which is 1 gram per ml. In this container also you can say density of water will remain 1 gram per ml. So if this value is not going to change after reducing the amount, after bifurcating it into two equal halves, it means that a property is going to be the intensive property. So most of the calculations we already know for the intensive properties, but there are different thermodynamic quantities which we need to understand. So basically if I talk about the analysis of this part, I can say temperature is not going to change. So if I have a pan in which 100 ml water is present and it is present at 100 degrees Celsius, if I divide that entire part into 50 ml, the temperature of the water is going to remain same, which is 100 degrees Celsius. So that temperature is the example of your intensive property. Just like that, you have a pressure. Pressure is basically force per unit area. If you are dividing the entire part into two equal halves, area is also divided. So definitely in that case, the pressure is going to remain as it is. In the same way, density, we already took the example of density. One main property of liquid, which is surface tension, melting point of a particular liquid, you can say boiling point of a particular liquid, and all the concentration terms generally, they are intensive properties. Just like that, we have a viscosity also. Okay, so that particularly depends upon the nature of the material we have taken or nature of the matter we are considering. So these properties are not going to change on bifurcation. They are independent of the amount of the substance. Okay, in the same way, if I talk about certain other properties, we have a specific term. So any molar property is an intensive property. We are going to learn that part, how these molar quantities are always intensive in nature. So basically, if I am defining a particular quantity for 1 mole of substance, that part is going to be your intensive property, like your molar conductance, like your molar enthalpy, like your molar heat capacity also. These properties are going to be intensive one. I hope this portion is clear to everyone. Very easy analysis. We are going to learn about each and every part. Don't worry that why we are not discussing about the molar conductance and molar enthalpy. We are going to discuss that particular part when the situation comes, when we are going to deal with that part only. Then I'll let you know what is the meaning of that term and how you are going to determine with the help of a particular formula. Okay, now talking about the next part, we have certain properties which are known as extensive properties. So basically these are the properties that depends upon the quantity of the matter present in the system. So always remember, in this case we are talking about the properties which depends upon the size. So for example, if I talk about the 100 ml of water, so in one container, let's say I have 100 ml water. Now I have bifurcated into two parts. So I can say in one container, now I have 50 ml of water, and in the next container I have again 50 ml of water. Now you can see initially I have started with 100 ml of water, which is the volume, which corresponds to the volume. Now after bifurcating, volume actually divides into two equal parts. In this case you can see the initial volume was 100 ml, but now it is bifurcated into 50 ml each. So basically it depends upon the quantity I have taken. So always remember, this volume term, this volume is going to be your extensive property. This is going to be your extensive property. So for example, if I talk about the volume, I already told you. In the same way, if I talk about the mass also, in the same way, now we have certain important terms in this scenario. Like we have a term which is internal energy, we have a term enthalpy, we have a term Gibbs free energy, we have a term entropy, we have a term which is heat capacity, not molar heat capacity, only heat capacity. These terms are going to be extensive property, and when we are going to discuss each and every property, then again I am going to recall like why they depends upon the quantity, because if you are changing the amount of the substance, definitely the values of internal energy, enthalpy, entropy, Gibbs free energy, or your heat capacity, these parts are going to change. I hope this entire portion is clear to everyone. It's an introduction session, so don't worry, everyone can listen to this lecture, everyone can understand what is going to happen in this particular chapter. So rest of the lectures are going to be very interesting one, because we are going to incorporate the calculation in that particular part. Okay, now let's coming back to the next part. If you are dividing two extensive properties, you are going to get an intensive property. So always remember, a ratio of extensive properties will give you an intensive property. That is the basic idea. That's the basic idea. Now what happens, for example, we have taken mass and volume, both are extensive in nature. So when I divide mass with volume, I get the value of density, and we know that density is an intensive property. Like these two, these are extensive properties. These two are extensive ones, but the density here is actually intensive property. I hope this part is clear. Just like that, molarity is basically number of moles per 1 liter solution, you can say, or divided by the volume of the solution. Again in this case, molarity is going to be your intensive property, but rest of the part, they are your extensive property. So this is a very interesting formulation. That's why the molar heat capacity is going to be the intensive one, while the heat capacity only is the extensive property. We are going to deal with the calculation part of heat capacity also, as well as the definition, but now in this lecture I am going to just give you the basic perspective related to this entire chapter, which is thermodynamics. I hope this part is clear. Just have a look at it. Okay, now coming back to the part, we have two type of functions. So basically how there is a origin of this state function as well as path function. So whenever we talk about any thermodynamic process, in that case, let's say we have an initial state from where we have started, like the initial state. Then I move to the final part. This is the final state of the system. So let's say I have started with a certain amount of gas, having a specific amount of pressure, having a specific amount of volume at a specific temperature. So in this case, I need to understand that for initial state, I need to explain this entire part with thermodynamic variables. So basically, thermodynamic variables are the variables which actually determines the state of that particular starting phase. So let's say I'm starting with gas and I need to convert that gas into liquid or directly into solid. So I need to understand that there are certain variables which can actually define a particular state. So these thermodynamic variables, they can actually define a particular state. And in that case, you know these variables, we already discussed this entire part in gaseous state. So basically we have a pressure, we have a volume, we have temperature, as well as we have amount of substance. So basically these are the important things. These are the most important things, P, V, T as well as N. So mostly we are going to deal with the P, V, T, but in certain cases also we are going to deal with N part. So this is the initial state and I want to convert that part into final state having again these thermodynamic variables, which is P, V, T as well as N. Although in both the cases this part is going to change. These thermodynamic variables are going to change. In first case, let's say I'm starting with gas, definitely in that case the gases are going to have a less amount of pressure, their volume is going to be very high at a particular temperature, and I want to convert that part into liquid having small amount of volume, pressure will be high at that particular case, the temperature is going to be specific, and whatever amount we have taken initially. So I can determine that initial state of the reaction was a gaseous state, and finally eventually after the completion of reaction we have converted the entire part into the liquid state. So that is initial state and that is final state. Now during this conversion there are different type of processes by which I can convert state 1 into state 2 or initial state into final state. There are different pathways. Either I can go directly by changing all the variables, or I can go by any path. So let's say this is a Q, some intermediate path, and then eventually it's going to be converted into final state. Let's say there are next part which is a P state, then we have R state, and then they are going to convert it into final state. So there are multiple methods, there are multiple ways by which you can change the initial state into final state. So that depends upon the type of processes we are talking about, but yeah, different pathways are always there. Now a state function is basically a property whose value does not depend upon the path taken to reach that specific function, but always depends upon initial and final state. It only and only depends upon the initial and final state. Doesn't matter like you are going directly or you are going indirectly or you are going with another pathway. So whenever you are going from initial to final state, their value always depends upon the initial as well as final state. It does not depend upon the pathway you have taken. That particular part is actually known as your state function. And in case of thermodynamics, we have mainly these type of state functions. So basically SUHAG, it's not Sohag, definitely. First part is S, which is known as entropy in case of thermodynamics. Then we have U, which is internal energy. Then we have H, which is known as enthalpy. Then we have A, which is known as Helmholtz free energy, and last part, which is G, known as Gibbs free energy. Okay, so these are some important parts, some important state functions of related to thermodynamics, which are SUHAG, and we are going to learn about each and every part. But remember, in this case, if I talk about the all the thermodynamic state functions, which is SUHAG, just note down one thing. It's impossible to calculate their exact value. So we are always concerned about their change. Okay, so in case of thermodynamics, you have to understand one thing, that it's actually not possible to calculate their exact value, because in case of internal energy, there are multiple factors which are going to contribute towards the internal energy. It's the vibration, it's the rotation, it's the translation, it's the electronic transition, whatever it is, it's somehow the potential energy of the system, somehow the kinetic energy of the system, that depends upon various factors. So it's not possible for you to calculate the exact value of these state functions, because they comprise of different type of parts, different type of energies, but it's much more feasible for you to calculate their change. So from state 1 to state 2, what is the change in the internal energy happening, so that part you can easily calculate. So that's why we are more concerned about their change calculation, and that's why, you know, if you know this chapter, whenever we talk about these parts, we generally talk about delta S, we talk about delta U, we talk about delta H, we talk about delta G, because we are more concerned about their changes rather than their exact value, and it's not feasible to calculate their exact value also. Okay, I hope this part is clear. I hope this entire portion is clear. So just like the part where we are going to talk about the state and final state as well as initial state, and independent of the pathway, there are certain functions also which depends upon the pathway. So let's say I'm moving from initial to final state, the change in that scenario is the same. The change from direct initial state to final state is exactly same. The change from initial to final state from this pathway is exactly going to be same. That is the meaning of state function, because it depends upon the initial and final state only. But there are certain functions also which depends upon the pathway, which actually depends upon the pathway. So in that case, path functions are the functions that depends upon the path taken to reach that specific value. So we have initial state. Let's say in this case we have P1, V1, T1 and N1. Let's say everything is changing, and I want to reach to state 2, which is final state. So either I can reach by direct part, or I can reach some intermediate then go towards this part, or I can go to two intermediate state then go to this particular part. Now in case of path function, whatever value I am calculating from state 1 to state 2 conversion, in this case let's say the pressure is P2, volume is V2, temperature is T2 and amount is N2. Let's say everything is changing. So there is one pathway which is the direct pathway, this is the next pathway, and this is the last pathway. Every time I am calculating for one pathway, the value is different. For second pathway, the value is again different. For third pathway, the value is again different. It means it depends upon the path taken to reach that specific value. That function is actually known as your path function. And generally, in terms of this thermodynamics, these path functions are basically heat as well as work done. I hope this part is clear. I hope this part is clear. I hope this entire portion is clear. So that is the basic meaning of the path function as well as basic meaning of state function. Now, like, I'm not talking about the calculation part, because first of all we have to understand what is the heat, what is work done, what is the meaning of these terms, entropy, internal energy, enthalpy, Gibbs free energy, Helmholtz free energy. We have to understand. So that is just the introduction part. That's why I told you that in lecture 1 we just need to be familiarized with every term whatever we are going to discuss in the upcoming session. Now if I talk about the thermodynamic processes, so for the state conversion from initial state to final state, how can I convert state 1 into state 2? What are the different pathways? That pathways are basically your thermodynamic processes. So basically processes which involve change in the state variable. Now you know the state variables, basically those variables which determines the state of a particular part. So basically variables which are going to determine the state whatever we have taken initially, that particular part corresponds to your state variable. And generally you know this part is basically your pressure, volume, temperature and amount of substance. Because now you have a keen idea about the gaseous state, you know about the change of pressure, change of temperature, change of volume as well as change of amount of substance, and each part corresponds to a specific type of process. Just remember Boyle's law, Charles' law, Gay-Lussac's law, so that you can correlate with that part. So first process is actually known as your isothermal process. So basically the process which occurs under constant temperature. So the process occurring at a constant temperature is basically your isothermal process. So basically in that case you can say change in temperature is 0. So there are certain graphs of isotherm. If you remember Boyle's law, there was a graph of P and V which is known as the isotherm, because in that case the temperature is constant. So in the same way, if I talk about the next part, we have isobaric process. So in this case the process is occurring under constant, isobar means pressure. So the process is occurring under a constant pressure. We are going to discuss about these processes and which quantity we want to calculate. So let's say I want to calculate work done under constant temperature. I want to calculate internal energy change under constant temperature. So that process will be isothermal process. I want to look at the change under constant pressure. That process is isobaric process. It means delta P in that case will be 0. I hope this part is clear. In the same way, we have isochoric process. Basically the process occurring under constant volume. So the process occurring under constant volume is actually known as your isochoric process. Delta V will be 0 in this case. In the same way, if I talk about the adiabatic process, this is the new process. This is a very new process. So basically adiabatic process in which heat is not going to change. Heat is not going to change. So basically in those processes, always remember delta Q will be equal to 0. There is no change in the heat. That process is a very interesting process known as adiabatic process. And remember, for JEE Advanced, most of the questions are somehow related to the adiabatic process. If you know, there is a specific relation or a specific ratio which is known as Poisson's ratio. So this Poisson's ratio always corresponds to adiabatic process, and most of the calculations are not that complicated, but their questions seems to be very confused. So this is the part where you get maximum questions from the advanced level, and we are going to discuss those questions also. Okay, so don't worry. Now last process is basically known as cyclic process. So just like a particular cycle, your initial and final point are exactly same. So you can say in this case that initial and final state, they are exactly same. So those processes are actually known as cyclic processes. So the state from where you have started, you took a pathway and eventually you reach to that same state after that. So that corresponds to your cyclic process. Again, a very important one. So in case of cyclic processes, when a system undergoes a number of different processes and finally returns back to its initial state, it is termed as cyclic process. Very interesting term, very interesting term related to the thermodynamics part. Okay, so basically in that case you can see all state functions or all state variables are going to be exactly same because there is no change. So let's say I have state A, and in this case we have a pressure 1, volume 1, temperature 1, and then amount of substance, let's say, is constant. So initially I have reached to state 2, which is B. In this case pressure becomes P2, volume is, let's say, V1, temperature is T2. So the process is occurring at constant volume. It means this process is isochoric process. Eventually I have converted this part into state C, where pressure is same, which is P2, volume becomes V2, temperature is now T2. So this process is occurring at constant pressure and temperature. It means in this case we are talking about the isothermal as well as isobaric process. Let's say this is a D part. In this case again the pressure goes to P1, volume remains same, let's say V2, and temperature is also changing, which is T1. So in this case the process is occurring at constant volume, which is isochoric process, and eventually I have reached to the same state. So in this case this process is going to be your this process is going to be your cyclic process. Now one thing in that case, that if this is a path function, definitely the value entirely depends upon the path. But if it is a state function which depends upon the initial and final state, if this function, whatever we are talking about a particular change which is happening, if that quantity is basically your state function, so the entire change for the cyclic process of the state function is going to be 0. So if I want to calculate any state function, in that case, their change will be 0, because in this case both initial and final states are same, and state function depends upon the initial and final state. If they are same, definitely you can say that change will be exactly 0. I hope this entire part is clear. So for cyclic process you can say delta S, delta U, delta H, delta G, delta A, everything is going to be 0. I hope this part is clear. So that is the basic idea about entire processes occurring in the case of thermodynamics. Now if I want to draw the curve, how can we draw the curve? So first of all you have to understand what is the meaning of that curve. The most confusing one is going to be the isothermal as well as adiabatic one. So I have a simple trick. I'll let you know what is the trick in that case. So let's say we have a curve. Let's say, or I can start here. Okay. So let's say this is the curve, and this curve is a very prominent curve which is P and V. So you will get to know that in the entire thermodynamics we are going to deal with this type of curve which is PV curve. Okay, because this curve talks about the work done also, PV work done, expansion of gas and compression of gas. So let's say if I talk about the process, so let's say initially the pressure was very high and volume was very low, and eventually the pressure starts decreasing and the volume starts increasing. There is also one process when the pressure starts decreasing and volume starts increasing. When the pressure is decreasing, volume is increasing, means you are talking about the expansion. So this curve corresponds to the expansion of gas. This curve corresponds to the expansion of gas. Okay. Now, how to determine that this process, which process is going to be isothermal and which process is going to be adiabatic? So, either you can calculate the work done, or you can calculate the part where you can see for one process the work done is more, for expansion process work done is more, for one process work done is less. But that requires the calculation. We need a trick. So, what you can do? You just go to the starting point. Just put your thumb on the starting position. Just put your thumb in the starting position and start moving clockwise. Whatever the value, whatever graph comes first, that graph corresponds to isothermal graph, the PV graph. And the next part, the graph which comes after, will be your adiabatic one. And we know, like this curve is also true, because we know that work done in case of gas expansion, work done for expansion for isothermal process is actually more in comparison to the adiabatic process. That part we are going to learn in the calculation part, but I am just giving you the basic idea that this curve is actually true. So that is the first part related to the expansion curve. Sir, what happens when we talk about the compression part? There is also a process of compression. So let's say in this case I can say this part is going to be isothermal and this part corresponds to adiabatic. adiabatic. Sir, is this true for compression also? So let's find out. This is the curve for expansion. Okay, expansion of gas. This curve is for expansion of gas. Now let's say in the second scenario, I am talking about the compression of gas. What is the meaning of compression? It means you are increasing the pressure and you are decreasing the volume. It means it will start to originate like this or like this type of curve. So the origin is there. So basically this is the curve for compression, that volume is decreasing and pressure is increasing. Sir, how to determine which process is adiabatic, which process is isothermal? Same trick. Just put your thumb on the origin part, move clockwise. Whatever comes first is your isothermal. This is your isothermal and this one will be adiabatic. I hope this entire part is clear to everyone. This is the meaning of the entire process. So I hope the chances of confusion are very less. This is a very simple trick you can try for this type of curve, because in certain cases of JEE, there were direct questions related to the graph, which graph corresponds to the isothermal part, which graph corresponds to the adiabatic. So it's the easiest way. Either for compression or the expansion, you can use the same trick. Just put the thumb on the starting position, origin position, and then move clockwise. Whatever comes first, that will be your isothermal part. Now you can see this process. So in this entire process, you can see the pressure is constant. It means this graph corresponds to isobaric process. Now you can see this curve also, So it means volume is constant. This part corresponds to isochoric process. So you can draw PV curve for each type of process. Either it is isobaric, either it is isochoric, either it is isothermal, or it is adiabatic process. I hope this entire part is clear. Okay. Now let's talk about the next part. What is reversible and irreversible process? So basically, reversible and irreversible processes are very different from each other. Basically, in that case of reversible process, you are talking about very small changes in finite time. So basically, this process is infinitesimally slow process. So in different infinite steps, this process is going to occur, but every time that change is a very slow. Okay, that's why it is somehow related to quasi-static process, because it's a very small process which is occurring in infinite number of steps. A reversible process is an infinitesimally slow process and takes infinite number of steps for the finite change. So let's say you are changing pressure and volume from one state to next state. So let's say I have this P1, V1, and I want to convert it into P2 and V2. Let's say this is a change. This is a finite change. This entire change is a finite change. But this change is occurring in infinite number of steps. This change is occurring in infinite number of steps. It means that a change, that a process is basically a reversible process. Every time, at every step, at each step, always remember that equilibrium is going to be established. Equilibrium is going to be established at every state, at every small change. And remember, in this case, if you are disturbing the system, if you are disturbing anything, then eventually it will reach to its initial state very quickly. So basically, in a reversible process, both system and surroundings are in thermodynamic equilibrium. This is the most important part. They are going to remain in thermodynamic equilibrium at every instant during the process. So basically, you are compressing a gas, but you are applying a very small amount of pressure. So initial pressure was, let's say, P1, and you have just included dP part. dP is very small fraction. So initial part is this, and you have just applied dp pressure. So this will become P1 plus a dp, which is very, very small. It means it's going to change its volume very, very, very slow in infinite number of steps, and eventually it will convert into, or it will reach the final state, which is a P2 and V2, by simply applying a small amount of pressure. That process corresponds to your reversible process. And always remember, in that case there will be a equilibrium establishment between system and surrounding every time the system is going to achieve the state of equilibrium. So in that case, at every step the system is in equilibrium with the system and surrounding. That is the thermodynamic equilibrium. But that case is not possible in case of irreversible processes, because in that case the change is very, very drastic. Basically, in case of reversible process, both system and surrounding are in thermodynamic equilibrium at every instant, and reversible process occurs when a pressure or a temperature difference between system and surrounding are very, very small. So basically I am changing the pressure, but the amount I am changing is a very, very small. So basically there is a gas which is present and there is a movable piston. Piston is basically, you must have seen the how can I say, there is some instrument which is used to fill the air inside a tire, inside a bicycle tire. So that part you are pressing and you are creating some high amount of pressure inside the air. So that is the piston you are moving. So this piston is present. There is one gas which is already present in the system, and that gas has a specific pressure. Now on that piston I am applying a very small amount of pressure, which is the P external. P external will be a small amount addition or subtraction from the P internal. That defines the state. Either it's going to be expansion or it's going to be a compression process. So basically that change is a very, very small. That corresponds to your reversible processes. Okay, I hope this part is clear. I hope this entire part is clear. Now in case of irreversible process, first of all, it's not a quasi-static process. It's not going to take infinite number of steps. It's a very fast process. It's a very fast process. So you have a gas. You initially applied that much amount of pressure that eventually it converted directly into liquid state. But you know, if you are removing that pressure, eventually the gas is not going to the liquid is not going to convert back into the gaseous state, because that process is now irreversible. So again, in case of irreversible process, there will be no establishment of equilibrium. There will be no establishment of equilibrium between system and surrounding. So you can say, unlike reversible processes always completes in a definite number of steps. Either you can use one step, two step, that process is going to complete. All naturally occurring processes are generally irreversible processes. These processes are generally irreversible processes. Now in irreversible processes, thermodynamic equilibrium does not exist at initial in every step, but it's going to be exist between initial and final state only. So not on multiple steps, not on those infinite steps, but again between initial and final state only. Okay. Now basically, when the path of a irreversible process is reversed, just like the reversible process, when the path is disturbed, again it will come back to its initial state. But in this case, this part is not possible. If you have converted liquid into gas, now after removing the pressure, you cannot get gas back. It is actually converted into the liquid state. So just remember, when the path is reversed, system and surrounding or both don't get back to their original state. That is the condition of irreversible process. Okay. Now there is a finite difference in pressure and temperature of the system and surrounding. So that's why we have taken a large change. So always remember, this corresponds to large change, and this part corresponds to very small change. Okay, that part is related to your mathematics, delta D. So that part corresponds to a very large and very small amount of change. So in case of reversible process, we generally use a dp, but in this case we use a delta p. I hope this part is clear. I hope this entire part is clear. Now they will be much more relevant when you are going to calculate work done for reversible process as well as irreversible process, because that is very confusing. So the calculation part will come in the first law of thermodynamics, because that part is the most important one. and the entire part we are going to discuss in the first portion of first law of thermodynamics. Okay, so don't worry, I'm going to give you the idea how to calculate the work done for reversible and irreversible process. This lecture is just the introduction part, so we are dealing with different type of definitions which we are going to discuss in the upcoming portions. Okay. Now after completing the entire part, you can see the difference between reversible as well as irreversible process very easily. This process is going to occur in infinite number of steps, but this process is going to occur in the finite steps. Now in this case, irreversible process is carried out rapidly and the difference between the driving force and the opposing force is quite large. But in this case, the driving force and the opposing force, they are approximately equal and the change is very small. Now it is complete in infinite number of steps, but the irreversible one completed in finite number of steps. Just like that, system and surrounding are always in equilibrium at every stage, but in this case they are only and only in equilibrium at initial as well as final state. In the same way, when the path of a reversible process is reversed, then eventually it will come back to its original state. It will come back to its original state, but in this case it doesn't go back to its original state. That's the difference between reversible and irreversible process, and reversible process are only imaginary. So just like the ideal gas equation, which is useful for the idealization, so that process is mostly imaginary and cannot be achieved in the actual practice or in the daily life experiments. But this process, we know that most of the phenomena which are occurring in daily life, they are related to the irreversible process. I hope this part is clear. So just like the states of matter, we have a specific system which is very ideal and there is a system which is not that ideal. Okay, I hope this part is clear. Now if I talk about the next part, we are going to talk about the work done. So basically work is said to have done whenever the point of application of a force is displaced in the direction of that particular force. That is the basic idea, that is the definition according to physics. I'm not saying that that definition is going to work with us, because our idea for work done is slightly different. Now in this case, if I talk about the W part, W is generally will be equal to F into dl, whatever displacement is happening, and I told you that work is a path function. So there are different type of work done. Either we can say that it's going to be electrical one, either it's going to be electrical work, or I can say it's going to be PV work done. It's going to be PV work. Now this PV work is much more relevant. What is the meaning of this PV work, sir? So basically in this case I am talking about the compression as well as expansion of gas. So whenever I am compressing a particular gas or the gas is expanding itself, in that case work is happening, some work done is happening, because it's going to change the position of the piston. Either the piston is going to go upward or it's going to go down. So that part, the pressure and volume both are changing, so that PV work is much more relevant to us. So definitely we are going to deal with the PV work done in the entire chapter. And if I talk about the units, in that case there are different units related to work done. Either you can use a joule, or you can use calorie, or you can use a liter ATM. These are the different units, or you can use erg also. So that is the basic idea about the work done. Why we are not discussing the calculation part now? Why I am not deriving the most common formula, your favorite formula, which is minus a P dV? So that part we are going to discuss in the next session with the calculation part. How we can determine that formula and how to apply that formula for reversible as well as irreversible type of reactions. Okay, so work of expansion and compression, or I can say the PV work, is more important to us. So this is the most important part of thermodynamics. We are not interested in electrical work now. That part will be done in electrochemistry itself. Okay, so it is the work done when the gas expands or contract against an external pressure. So that part is very relevant, and that's why you know that there is a formula which is minus a P dV. I'm not deriving the formula, but I'm just giving you the idea that this is going to be the work done. We are going to discuss that part also in first law of thermodynamics. Okay. So that is the formula which comes out after the entire calculation. We are going to derive. Don't worry. I am going to give you the idea how to derive this particular formula. I have just written the formula here because it's a very familiar formula for you guys, which is minus a P dV. Okay, now in this case, work is basically, there are two things. Either the gas is going to be compressed, it means you are working on the gas, you are applying the pressure and gas is actually compressing. Or next part is gas is expanding itself. So when the system is going to work, or second part, when we are doing work on the system. So basically when the work is done on the system, just like the compression part from the surrounding, W is going to be negative. Okay, next part, when we are working on the system. So basically there are two things I already told you. When the system is again going to work itself, or we are working on the system. So when the system is working by its own, it means W is negative. When we are working on the system against its actual will, we are working on that particular part, that W is going to be positive. That is the sign convention related to the part of work done. So on the system and by the system. So by the system is always negative. On the system, it's going to be always positive. I hope this part is clear. Generally in chemistry, we deal with the by the system itself, but in case of physics, generally we deal with the on the system part, because we are dealing with machineries and we are working on that particular system. So that's why you know that the work done in chemistry is slightly different, in the sign convention is slightly different from physics work done. Okay, I hope this entire portion is clear to everyone. Now if I talk about the heat part also, I am just giving you the basic idea, the definition part. Heat is defined as the energy. So there are two modes of transfer of energy. So basically if I talk about the modes of transfer of energy, whatever energy is present in the system, either it's internal energy or any type of energy I am considering, there are two modes. So first one is basically work done, and second part in that case is heat. Either system can utilize its heat change, or it can transfer its heat into work done. It can utilize that part into the work done, expansion, compression, whatever it is, or it can utilize the entire part and dissipate some amount of heat. So basically there are two modes of transfer of energy. The second mode is basically heat. So basically it is the energy that flows in or out of the system because of the difference in the temperature between the thermodynamic system and surrounding. When there is no PV work, when nothing is compressing, nothing is expanding, I can say that entire amount of heat change, entire amount of energy change is going to be released in terms of heat. That is basically due to the difference between the temperature of system and surrounding. If that part is not possible, definitely system is going to utilize that part for work done, PV work done. Okay, so again its unit is going to be just like work done, calorie, joule, erg, atm, liter, and you know that 1 calorie is basically approximately equal to 4.2 joules, 1 liter atm is 24.206 joule, and 1 joule is basically 10 raised to the power 7 ergs. So that is the basic idea related to the conversions. I hope up to that part everything is clear to everyone, and we have discussed like everything. So if you want to define this symbol of heat, this is generally Q. Okay, so that is the basic part related to your chapter, which is thermodynamics. So just like the work done part, on the system, by the system, we have the same type of sign convention for heat also. When heat is dissipated by the system, when the heat is released, we generally take it as a negative. It means heat is given out to the surrounding. When heat is absorbed, it means Q is going to be positive. Now combining each and every part, we can say this is the system. Either system can do work by its own, or we can work on the system. So when the system is doing work by its own, W is negative. When we are working on the system, it's basically positive. When system is releasing heat into the surrounding, it's going to be negative term. When system is absorbing the heat, it's going to be positive term. So that is the entire sign convention with respect to system as well as surroundings. I hope this entire portion is clear to everyone. Although we have certain terms also, which is a heat capacity, molar heat capacity, but that part will be much more relevant when we are going to discuss about the calculation. Okay, so I guess that is all related to this entire portion, which is the basic portion of your chapter. Now next lecture is going to be very interesting, because we are going to start the first part, which is first law of thermodynamics and calculation of work done and heat for different type of processes. First of all, we are going to learn about the work done calculation, how this work done is working for reversible, irreversible processes, how we can calculate this entire part, expansion and compression part. Then we are going to move on to the next part, which is internal energy change for different type of processes, isothermal, isobaric, isochoric process, adiabatic process, just like that. And then we are going to talk about the cumulation of the entire part, which is basically your first law of thermodynamics. So the next session is going to be very interesting one, and definitely it's we are going to have lots of questions related to the entire part. So I can suggest you one thing. Meanwhile, you can just simply read first 3-4 pages of NCERT, where you can find each and every information just for the clarification, so that you can get the crisp entire part or the gist of the first lecture, whatever we have discussed. Okay, so I guess that's all from my side. We are going to discuss the next part in the next lecture. Okay, so bye bye everyone, thank you.